Imagine you're on a starship, coasting in the dark between the stars. No planets nearby, no landmarks, just endless black. If your navigation system slips by even a billionth of a second, your ship could drift millions of kilometers off course. Now imagine scientists have just found a way to bend the rules of quantum physics to make a clock so precise it could guide that starship through the void almost perfectly. In this video, we're going to unpack how a new loophole in quantum physics could supercharge atomic clocks, turn them into the ultimate cosmic GPS, and maybe even help us probe dark matter or predict earthquakes here on Earth. All in plain language, no PhD required. Before we jump into the quantum weirdness, tap subscribe and hit like so you don't miss more deep dive space stories like this one. It tells YouTube this kind of content matters and really helps the channel grow. Let's start with something familiar, the GPS in your phone. When you follow that blue arrow on a road trip, your phone is constantly listening to signals from satellites far above you. Each of those satellites carries an atomic clock on board, and by comparing the arrival time of their signals, the system can pinpoint your position on Earth to within a few meters. Those clocks are so stable they'd gain or lose only about a second over something like 10 million years. Normal clocks tick using gears or vibrating crystals. Atomic clocks tick using atoms themselves. Inside, atoms like rubidium, strontium, or ytterbium are blasted with carefully tuned electromagnetic waves, and their electrons jump between energy levels at astonishingly regular frequencies. Count those oscillations, and you have a time standard that barely drifts at all. The most advanced versions are called optical atomic clocks. Instead of ticking in the microwave range like older atomic clocks, they tick with light. Atoms such as ytterbium vibrate so fast, hundreds of trillions of times per second, that these clocks can, in principle, measure time intervals unimaginably smaller than anything we deal with in daily life. That's the level of precision you'd want if you were trying to navigate not just around Earth, but across the solar system and beyond. But there's a catch. At this level of precision, the universe itself starts to fight back. Quantum mechanics says there's a fundamental limit to how precisely you can measure certain properties at the same time. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. That uncertainty shows up as what physicists call quantum noise, a built-in fuzziness that blurs your measurement. For decades, clock builders have tried to beat this by simply using more atoms. If each atom is a bit noisy, then averaging over many of them gives you a cleaner signal. But you can't do that forever. There's a standard quantum limit that says, for a given number of particles, there's only so much precision you can squeeze out. Here's where the new research comes in. One team of physicists working with ytterbium optical clocks has shown that you can use quantum entanglement to push past that usual limit. Instead of each atom behaving like a separate, jittery little clock, they use carefully designed laser light to link the atoms together into a collective quantum state, a synchronized superatom. When you measure this entangled bunch, you can extract more information about the clock's tick than you could from the same number of atoms acting independently, roughly doubling the precision without adding more atoms. Meanwhile, researchers in Australia have attacked the problem from a different angle. Instead of entangling atoms, they've found a way to tiptoe around the usual uncertainty limits by being extremely picky about what they measure. Normally, if you try to measure both the position and momentum of a quantum system, you slam into Heisenberg's wall. Get one sharply and the other blurs. Their trick is to ignore the big picture and focus only on tiny changes. Imagine a clock face that doesn't bother telling you which hour it is, but can tell you the exact second with incredible sensitivity. You lose some global information, but for detecting small shifts, the kind that matter to an atomic clock, you gain a whole new level of precision. This isn't breaking quantum mechanics, it's playing within the rules, but in a clever way. By throwing away certain kinds of information, they can measure the delicate motion of ions inside a clock far more accurately. That's especially important for a new breed of atomic clocks that use highly charged ions, which could be even more accurate and stable than today's best devices, but are notoriously hard to read out. The new method gives us a sharper lens to see what those ions are doing, and that sharper lens translates directly into a better clock. If you're enjoying this tour through the bleeding edge of quantum timekeeping, take a second to press like, drop a comment with your favorite mind-bending physics idea, and share this video with a friend who loves space and science. It really helps me keep making videos like this. So what does all of this have to do with interstellar travel? To navigate anywhere, you need two things: a map and a way to know exactly where you are on that map. On Earth, our map is built into GPS satellites and ground stations. The way we know where we are is by measuring how long it takes radio pulses to travel between those satellites and our receivers. Because nothing outruns light, measuring time with ridiculous precision is effectively the same as measuring distance with ridiculous precision. In deep space, the same logic applies. Spacecraft talk to Earth using radio signals, and giant antennas measure tiny timing shifts in those signals to track where the spacecraft are and how fast they're moving. But this still depends heavily on Earth-based infrastructure. If you want a ship to navigate on its own far from home, you need clocks on board that are so stable they can serve as miniature lighthouses of time in the cosmic dark. Ultra-precise quantum-enhanced clocks could be that lighthouse. Imagine a future probe headed to another star, carrying its own compact optical clock, entangled atoms ticking away in nearly perfect synchrony. Back in our solar system, a network of similar clocks might orbit the sun or sit on distant moons and planets. The spacecraft would listen for their signals, compare them with its internal clock, and compute its position with extraordinary accuracy. No constant guidance from Earth required. Push this idea even further, and you get a kind of interstellar GPS, a mesh of time beacons that let any ship with a good receiver know exactly where it is, anywhere within that network. The better the clocks, the fewer beacons you need, and the farther out you can go before the uncertainty balloons. And it's not just about navigation. When clocks get this good, they become sensors for the universe itself. Tiny changes in gravity, the passage of mysterious dark matter, or the slow stretching of space-time in a gravitational wave can nudge a clock's tick by a fraction of a second and reveal subtle shifts in the world around us. We're not there yet. These experiments are happening in carefully controlled labs, not on board starships. But the principle has been proven. By entangling atoms and by cleverly rethinking what we measure and what we throw away, physicists have shown that our best clocks can get even better, far beyond what we once thought was the quantum limit. If breakthroughs like this fascinate you and you want to ride along as we explore the technologies that could actually make interstellar navigation possible, make sure you're subscribed with notifications on. Smash the like button if this gave you a new appreciation for time itself. And tell me in the comments, if you had a ship that could navigate anywhere in the galaxy thanks to a clock like this, where would you go first? Thanks for watching, and I'll see you in the next one.